I'm Linda, and this is my stable matching module reflection for algorithms. So the main idea behind stable matching is, given an input, which is a preference list for proposers and receivers, can we make an output, which is a stable matching that satisfies the majority? First off, I have matching, which is a set of pairs where each proposer/receiver participates at most in one pair. Next up, I have perfect matching, which is where each proposer/receiver is in exactly one pair. And lastly, I have instability, or also known as an unstable pair, which is a pair such as P1R1 that is not found in M, but it follows that P1 and R2 is a pair in M, but P1 prefers R1 to R2, and P2 and R1 are a pair in M, but R1 prefers P1 to P2. So the main idea behind that, we see P1 prefers R1 and R1 prefers P1, but we see that the pair P1-R1 is not found in M. So the P1-R1 elements that prefer each other are not in a pair with each other, and that's what makes it unstable. So one algorithm that we learned is the Gale-Shapley algorithm. So the main idea here is that we first initialize all proposers and receivers as free, and then we have a while loop to go through each one. So while some proposer is free and hasn't proposed to every receiver yet, we first choose one of those proposers, and then we let R be the highest ranked receiver P has not yet proposed to. And so if this R is free, the P and the R become committed. But there's another scenario where the R that is the highest ranked for P is committed to a different P, and so we have another if-else statement branching off of that one, which is where either the R prefers the original P, so then this different P becomes free, and the original P and the R become committed. So basically, the receiver replaces the old P with this new P, and the old P becomes free for another future pair. But if this R prefers the P that it is already paired with, then the R rejects this new P, and the P remains free for a different match. And so this will continue looping until the condition is met, and by the end of the condition, all elements should be in a pair. And that goes on to the facts that I have listed below. So the first fact is that once matched, a receiver stays matched and only upgrades during the algorithm. So once a proposer and a receiver are in a pair, a receiver will stay with that proposer unless a new proposer comes along that the receiver prefers better, and so it will upgrade. But it will never lose its proposer without being in a pair. And then the second fact is that each proposer proposes in order of preference. So if a proposer prefers the receiver in order of R1, R2, R3, it'll first propose to R1, and if that doesn't work out, it'll propose to R2, and if that one doesn't work out, it'll then propose to R3. So next up, I have an example, and I decided to go along with Pokemon for my scenario. So the question follows is, today is Ash's 11th birthday. Congrats! Professor Oak has some Pokemon waiting, so Ash can begin a new adventure. Uh-oh, he broke his alarm clock in his sleep. Thus, out of 3 new trainers, he arrived last. Too bad that his longtime rival, Gary, got there first. Guess that means Gary gets first pick. No matter. 3 great Pokeballs are just waiting to be chosen. Except, there's a twist. A Pokemon won't accept being chosen unless it approves of its trainer. Otherwise, it'll run away. How can we pair 3 trainers and Pokemon so that the majority is satisfied, and without having any Pokemon run away? So here we have the trainers, which in this scenario are the proposers, and then we have the Pokemon below that, which are the receivers. And below each of the names, we see their rankings. So if we follow the Gale-Shapley algorithm, this last side is basically initializing all the proposers and receivers and setting them as free. And so here we begin going through the loop. So we chose a proposer P in this scenario, which is Gary, and we see that his highest ranked receiver is Squirtle. And we know that Squirtle right now is free, so Gary and Squirtle become committed. Next up, we choose a different proposer, in this case it's Red, and we look at his highest ranked receiver, which is Charmander, and since Charmander is currently free, so Charmander and Red become a committed pair. Next up, we choose our last proposer, Ash, and we look at his highest ranked receiver, which is Charmander, except we know that Charmander is already in a pair with Red. So we skip the first part of the if-else statement and we go to the else, where Charmander is already committed to Red. And so now we can look at Charmander's ranked proposers, and we see that Charmander actually prefers Ash over Red. So in this case, Red now becomes free, and Ash and Charmander become a committed pair instead. So now we return back to Red because although he was in a pair before, Ash took his place, so now he is free. So we look at his highest ranked receiver that Red has not already proposed to. So instead of Charmander, it is now Bulbasaur. And we know that Bulbasaur is free. So Red and Bulbasaur now become a committed pair. And so that while loop now terminates because every proposer and receiver is now in a perfect matching. And if we look at the preferences and rankings for each of our pairs, we can see that there are no unstable pairs because each proposer paired with their highest ranking receiver and only got replaced if the receiver preferred a different proposer over them and kind of upgraded. But although it upgraded and it may not be their highest ranked receiver, it is still not considered an unstable pair because, like, for example, Red and Charmander to have been an unstable pair, Red would have to prefer Charmander, but Charmander would also have to prefer Red, but he didn't, so that doesn't make it an unstable pair. So we see all these conditions have been met, we see the final pairings, they're all in a perfect match, and there's no instability, so therefore the algorithm terminates and we have our stable matching.